Hi, I'm Jonathan Oxer and this is SuperHouse. Now when we did some major renovations on this house a couple of years ago, we extended from the back wall of the house. This whole section I'm standing in now is new. It wasn't originally part of the structure and it's an incredible room. It looks fantastic. Whenever people come over for the first time, they look at this room and go, wow, that's amazing. But we found that we don't really use it all that much, basically because it acts like a big glass house. This whole thing turns into an oven. It's like a solar oven in summer. The sun just comes streaming in, this room heats up, and you can't really sit out here. What we need to do is get better ventilation through here. When the builder put this frame in, they allowed for windows. So 4 of these windows actually are hinged and can open up. Oh look, can you see this one's just blown open? That is exactly my problem. So for the last, I think, 4 years, these windows have just been held closed by little wedges of wood or bits of cardboard jammed in them. And whenever we have a good strong wind, the windows pop open. And of course, it usually happens at about 2 o'clock in the morning when there's a thunderstorm, it's dark, and there's wind and there's rain coming down. And I end up stumbling out here and trying to find some thongs to put on so I can walk through the mud. And then I use my phone as a torch so I can try to find the bit of wood that's lying on the ground in the dark and then jam it all closed and then walk in wet. It's horrible. So I need window winders. And when this frame was being put in, we actually allowed for it. As the builder was assembling the aluminium frame, I ran some mains flex cable and some Cat 5 cable and looped it around to all of the places I wanted to put the window winders. Now I was thinking ahead, but I didn't actually know what winders I was going to need. That's why I put both the mains flex and the Cat 5 cable. I didn't know whether I would need 2 40-volt winders or whatever. And in the years since, I haven't been able to find anything that would be suitable as winders. But I've just come across some that look ideal. The thing is, they actually work off battery power, so I don't even need mains power to them, and they use an infrared remote control. But they also have support for what's called LIN bus, which is local interconnect network, which is typically used in cars for communication between different devices. For example, it's used to send commands to power window motors, and these window winders that I've found support LIN, so it's perfect. So I'm going to try hooking up these window winders. Well, actually, the first thing I'm going to do is hook one up to an Arduino and see if I can control it using a LIN interface adapter, and then I'm going to mount them on the windows, and then we'll be able to get some natural ventilation through here instead of having it just heating up all the time. So the window mechanism that I found is in here, and it's actually a bit of a fluke that I ended up getting it. I wasn't looking for it in particular. There is a supplier here in Melbourne, a distributor for electronic parts, and they supply these little DC-DC converter modules that I use when I'm making these power over Ethernet adapters. And a little while ago I went down there to pick up a box of a couple of hundred DC-DC converters, and when I walked in the front, they had a display with a few different things in there, including some window frames and mechanisms on it. And I asked them about it and said, what are those? I could use those for my home automation system. And they said, oh, window winders. Perfect. So I've grabbed a few and I'm going to try them out. I've already opened one, but just so you can see exactly what you get, I'm going to start with a brand new one here in the box. Comes with instructions, of course, and then a plastic cover, so this is what goes over it. So these are available in both white and also like a silvery grey finish. I've got white window frames, as you've seen, so I've grabbed some of the white ones. There's a remote control. It's an infrared remote control, it's not RF, so we could probably do something like mimic the RF codes to control it, but we'll use LIN bus, as you'll see in a second. Got a bunch of assorted mounting hardware, some brackets that we'll get to in a second. Comes with the batteries. Oh, they're actually AXA branded batteries. This is an AXA remote control, so they've got their own batteries with it as well. That is a template. It's like a cutting guide that you use on the window frame, and that's the mechanism. So let's get all this stuff out of the way and start playing with it. So first thing I'll do is put some batteries in here. Actually no, first thing I will do is I will put batteries in the remote control, because when this first starts up, it begins in a learning mode I want to make sure that I'm ready to send the signal just when I power up this. Okay, so the receiver is just in here. It's the little infrared receiver that you can just see there, and that's the transmitter. So now I will put the final batteries in, and it should start in learning mode. Now I aim this at it, press stop, just press a few buttons, see what happens. It's now bound to the remote. And what it's doing is running through, it's exercising itself. It's just running the motors to make sure that it's all responding properly the first time. Now, if you look down here, you can see one of the interesting things about this is that this is the mechanism that comes out. That's the chain that you see on a typical window winder. It's now pushing the chain out. But there is also another mechanism in here, which is a lock. This is the bracket that goes on the window frame, and this little thing clips in here, and that screws onto the frame. So if you're looking at it from above, the window frame would be on here. You see where this little tab comes out with this pin, and there is a matching hole in the side here. There is one motor that drives this chain in and out, so that opens and closes the window, but there is another motor in here which has a little plate that runs inside the case, and what happens is that when the window closes, this part of the mechanism goes into this slot, and then the second motor engages and it slides 2 fingers along and it hooks behind this pin, so it positively locks it. So the end result is that the window is not just being held closed by the chain or the friction in the gearbox and the motor, which someone could possibly overcome by grabbing the window and really wrenching it open. It's positively held by the mechanism. So this comes in here, slides closed, and then the lock mechanism slides along. In fact, what I'll do is hit lock, so close, and we'll see what happens. So the chain is sliding in, and once it gets all the way through, which will take a little while, this will slide across. So while that's happening, there are a couple of other things here. This is part of the mounting bracket. The idea is you screw this onto the frame, and then this slides onto it. So you can see this little mating thing on here, and that can be used for adjusting the position of it. So this is positively mounted on the frame, and then this clips in. Alright, so this is nearly in. Watch what happens just in here. So it's now fully retracted. And now the other motor is engaged, and you can see inside there it's sliding across. And if this had actually been attached to the window, this mechanism would be inside and it would be engaging on this lock. And that way you can't possibly get the window open while it's locked. That's pretty cool. And as you can see, this is working totally off batteries. So you can screw this onto the window frame, clip the cover over it, mount this bracket on the window, and then just control it with the infrared remote. And that in itself is pretty cool, because it means that installation for a basic system is pretty easy. But what really got my attention with this, and what makes it interesting, is that on the end it has these little 6P 6C connectors. So I'll just bring it up here so you can see it a bit better. See if we can get some focus happening on there. So there are 2 connectors with 6 connections each, and that is a LIN interface. So LIN is Local Interconnect Network, and what that allows is a single master and multiple slaves on a serial communications bus. And what you can do is basically have communications with just 3 wires. You just need positive, negative, and data. What I'm going to do is try hooking up to the LIN interface. Now the importer that I bought these from had wanted to connect these to an Arduino, and he hadn't quite got it working, but he did have one of these shields, and this is a home LIN bus translator shield. It's got little connectors on there, and this shield is actually specifically designed for working with these remote controls. So on the shield itself there's this little interface IC that's I think an MCP2003. What that does is take serial communications in one side, like just regular TTL level, and it provides the interface on the other side to the 12 volt data line that's available on LIN bus. This is a microcontroller. What is that? I think it's a PIC microcontroller. And the way this particular shield works, it's quite interesting. It uses a number of the digital pins on the Arduino as inputs and outputs, and then inside this little PIC it takes care of sending and receiving messages on the LIN bus. So what you do is just plug this into an Arduino, and if, for example, you want to send a message that is open the window, you just assert one of the pins, like you drive it high for a few milliseconds and then release it again. That's detected by the PIC, which then formulates the correct message to send out in the LIN bus, and it sends it, gets a response back, and then responses such as a window status, like whether it's open or closed, is exposed on another data pin. So it'll take a pin high or low, so your Arduino can just read from that pin to see the status of things that are out on the LIN network. So it means that your Arduino only ever has to read and write digital pins to send commands. So there's a pin dedicated to lock, which is closed, one to unlock or open, and one to stop. So 3 pins for that purpose, and then another pin for the purpose of detecting the status, like whether it's open or closed or whatever. So that's kind of handy, and you just feed power in here, and then the data connection comes out on here. Now, the way this little 6P6C connection works is that they wanted to make sure that it was reversible and that there was no problem with getting the cable swapped over when you're crimping the connectors on. So what they did was pretty cool. There are 6 connections, and starting from the top, they made it positive, negative, data, data, negative, positive, which means it's symmetrical. So the 2 outer pins are connected together, and then the next 2 pins in are connected together, and then the middle pins are connected together. So you effectively get three lines with the 6 connections, but it doesn't matter if you reverse it. So you can get the cable and crimp it totally the wrong way, plug it in, and it will still work. That's pretty handy. So to test this out, what I've done is written a little sketch that runs on the Arduino, and it just provides an interface on the serial connection. So when you open up the serial console, it gives you a menu, and you can select open, close, stop, and it just pulses the appropriate pin. Very simple. So what I'm going to do now is just use the LIN bus shield connected to the Arduino, and now we will connect it all up. So down here I have a bit of ribbon cable, not ribbon cable, it's that like flat flex cable with 6P6C connectors on it. Just plug one in there, and also the other thing is very important, I've removed the batteries from here. That's because once this is plugged in and running over the LIN connection, I'll plug it into the shield here, the shield is actually going to supply power from this DC input down the LIN cable to power this. And this particular thing doesn't know how to handle having power both from batteries and from the connection. And when I was testing this a little while ago, I plugged it in on the bench power supply. In fact, I've got that right here. So I'll power that up, and also plug in the USB cable to the Arduino. And because it's just powered up, it's going through its little test exercise cycle. But what I did was, because this is running on a bench power supply, it's got a current limiting thing on it and a little ammeter, and I was wondering why it was drawing heaps of current when this was just sitting here doing nothing. And then I realized that it's because it was trying to feed power to the batteries, and if I'd left them in there for too long, they could have overheated or leaked or something, so that's bad news. So make sure that you don't have any batteries in this if you are connecting it up to the LIN cable, as I've got now. So I'll just leave that out there. So right now we have the Arduino connected by USB to my computer. It's got the LIN adapter running the sketch to provide the menu on the USB connection. That cable goes around to the opener, and I've got power coming in from a bench power supply. So it's providing power over the cable. The remote control, I'm not using it right now. So I'll just slide over to my computer. So if I now press close, it should send a command to the LIN device. There we go. So I'll send stop and open, close, stop. So I now have control over this from the LIN connection, and it's also providing power. Now that's exactly what I want for my system. Because I've got those cables in the frame already, I've got that Cat5 cable. What I can do is just cut that, put an RJ12 connector on it, and use that for communication with these motors. First thing though is I'm going to have to physically mount the motors on the window frames and get them working. I can prove that they work just with the remote control before I even do any network connection. I have to make a decision about how I'm going to mount this. I've got two options. When I was putting the cabling in, I assumed that what I would do is mount the motor up on the side here, so it'll be a vertical mount. And that's where the cable comes out. And I could also put it down the bottom. Now the thing is that this is as far as the cable extends. It doesn't really come out very far, which means that if it's put here vertically, that is as far as the window is going to open. It's only going to go to the extent of the cable. So I'll only get maybe 10 or 12 centimeters of opening on the window. So that's okay. I don't actually really want the windows to swing wide open. I just want them open enough to get some airflow through here and get some natural ventilation happening. But of course, because of the geometry of the window, if I mounted this on the bottom down here, the window would end up open probably twice as much because the chain extends to the center of the window frame and not to the edge of the window frame. So if I was doing this now, what I would probably do is mount this on the bottom of the window, but the problem is that I've already got this big hole here, so what I would need to do is cut off this cable and cover it up, and there'd be an ugly patch or something. I could probably do a reasonable job and you wouldn't see it very much, but it would still be there. So, and also what I would have to do is drill down through here and get cable down through the wall and come out under the house, which would be possible, but it would be a bit of work. So I think what I'm going to do is mount it vertically. It's probably the second choice. It's not the ideal option, but that way all of the cabling will be concealed and this will be up out of the way. So I think it'll be fine. And now a bit of white nail polish to seal up the edge of the metal. Should stop it rusting. This is a drilling bracket. The idea is that what you do is locate the position on the frame where you want to mount the motor, and then put this in here, and then just mark through the appropriate holes, and then you can just drill into those spots and everything should fit perfectly. So I have the mounting holes now for the motor, and what I've done is put this little drilling guide in place and screwed it in through the holes where the motor normally mounts. And what I can now do is use this to mark on the window frame where the holes need to go for mounting the bracket. So now I've got it all physically mounted in place. The mechanism itself is here. I've got the cable coming through for power and LIN bus. I'm not actually going to connect that right now. Just to test it, I'm going to stick the batteries in it, use the infrared remote control, make sure that it all works. There's this little clip on the top here. It just pops onto the top of this bracket, latches on. If you ever want to take this off in order to clean the window or whatever, you just pull back this little section, pop it off, and now the window is clear. Now one of the decisions that I had to make was how to clear this edge, and as you saw I used an angle grinder to cut part of that away and then mount this directly against the window frame. What I could also have done is put a spacer in here so that it raised it away from the frame, and then the chain would have cleared this bracket and I wouldn't have had to cut anything. But there was a very specific reason I left it like this. Now when the window is closed, with this being a wide bracket, I wanted to keep it visually within the line of the window. If I put a spacer on it and mounted it further out here, when the window is closed, you would see the bulge of the motor sticking out and obscuring the view. and that would ruin the look of, the panoramic view of all of these windows, little motor bulges sticking out. So as you can see, the end result is pretty nice. It's very low profile, and it pretty much disappears into the window frame, which is great. So I just need to do this to all of the other windows, hook up the LIN bus, and see how we go with that. Now, I keep talking about LIN bus as being a serial bus, but what does that mean? And what's the difference between a serial bus and just a regular serial link? Well, think about it this way. A normal serial link allows you to have communication between two different devices. It's like you pick up your phone, you make a phone call, and you are talking to one person on the other end of the line. And you can both talk to each other, so you can send messages in both directions. But it's only like a two-party thing. It's a direct link. If you look at the diagram, it looks like this. So we have party 1 down the other end, we have party 2, and we have a serial connection, which is a bidirectional link between them. But a bus is different. Instead of having just like two people on the phone talking to each other, if you've been on a conference call, it's basically like that. What you do is you have a whole lot of people all on the same phone call at the same time, and any of you can talk, so you can send messages and everybody hears it. So if we look at it in a diagram, once again, it's like this. So once again, we might start with person 1, and then instead of having simply a point-to-point link like this, we might have a series of people. So we might have person 2, person 3, person 4, and they are all connected to this same communications bus. So with a normal serial link, you can send messages just between these two. With a communications bus, any of these different nodes can send messages that the other nodes can hear. And just like on a conference call, you usually have an organizer. So, when a conference call starts, it'll say the organizer has joined or whatever, and then all of the other participants. The organizer is the one who controls it. With a communications bus, it's usually the same thing. There is typically a master or a host, and then there will be slaves. So the slaves are just like the regular conference call participants. And in a lot of buses, you can have the control, so the master pass from one node to another. And you can have different nodes on the bus initiate communication. So one of them might be a sensor that detects something. It can pipe up and say, hey, I've got a reading, here it is, and then everybody else on the bus hears it. But with LIN bus, it's designed to be an incredibly simple bus, and it's meant to be low cost, easy to implement for car-based systems and industrial systems as well, but it's primarily for cars. And it's a single master, up to 15 slaves, so you can have a total of 16 nodes, and only the master can initiate communications. So when there is a new message to send out, the master sends the message, all of the slaves receive it, and they can respond, but they can't initiate a message. So it's useful if you want to do something like send commands to things and then just make sure that they've received it with an acknowledgement, or if you want to do something like poll a sensor and then get a result back. But it's quite limited. But it is really useful in a situation where you have multiple devices. Because this is LIN bus in these motors, what we can do is connect multiple motors up together if you had like a series of windows, and I've got 4 windows in the conservatory where I'm fitting these, we can connect up 4 different motors, put them all on the same LIN bus and control them at the same time. So here we have a single motor connected to the Arduino with the LIN bus shield on it, and this is basically behaving like a direct serial connection, as you can see in this diagram that I did. So we've got one link from the master going down here to the slave. But these motors have a pair of connectors on the end, and that's really just a jumper through. The connections are linked internally, so that it means you can plug 2 cables in there. So let's grab a couple more motors and we'll link them up. I've got the power turned off at the moment. This Arduino is running, but power is turned off to the LIN bus. So I'll stick another little cable in here, jumper it across to the next motor, and then do the same to the third motor. So we now have all 3 of these motors and the master all on the same LIN bus connection, because these links just bridge straight through. So if we send a command now, any of these nodes should be able to hear it. I'll turn on power for the different motors, and they need to go through their wake up sequence because they need to check that they're actually okay. So I'll send a command. and you can see that they're all moving. They've all started doing their little warm-up. They're exercising the lock motors at the moment, so we've got to wait for that to finish. This one started a bit behind the others. It's almost finished. So once these are done, we should now be able to control these. So I'll just slide over to my computer and I will send an open command and we'll see if they respond. They're now running their little unlock mechanism, and as you can see, they're all extruding their chain. So if we had these connected to 3 different windows at the moment, all 3 of those windows would be opening. And if I send a stop command or a close command, then they will all respond as well. So all of these motors are operating in harmony. Now, as far as I can tell, what's happening is that the open, close and stop commands that are being sent by the master using that LIN bus shield on the Arduino are being picked up by all the nodes. So if I had 4 of these motors on here to do the 4 windows on the conservatory, I could send an open command and all the windows would open. Now, if I didn't want individual control, that would be fine, but as far as I know, I can't send a command just to say node 1 on the bus and then have it respond. Well, technically LIN bus supports that, but it looks like the firmware in these particular window motors doesn't support it. So I've got 2 options really. What I can do is either just put up with that, and any command that I send will make all of the windows open. The thing is that I can imagine situations where I might want to just open one window, or I might want to check the open status on one window, because if the windows are obstructed, they will stop and then back off, and it's possible to get the status of a window over LIN bus. One of the commands that I can send through that LIN bus shield is, what is your lock status or open status, and that node will respond. But if I can't talk to the nodes individually, then I can't get individual window status. So I'm not really satisfied with that. I want to be able to have direct control and status reporting over each of the windows individually. And I've come up with a plan for how I can do it. Basically, I'm going to treat these as point-to-point links, and I'm going to run 4 separate LIN buses. So if you remember, the cable that I had hanging out at the wall in the conservatory is Ethernet cable. It's like this, it's Cat5 cable. So inside Cat5 cable there are 4 pairs, and this is my general plan. I'll see if this works. What I'm going to do is use one of the pairs to carry positive, one of the pairs to carry negative. So that will carry power around to all of the nodes. That then leaves me with another 2 pairs that I can use. So what I can do is separate those and use those for 4 separate LIN bus connections. So what I can do is connect the first motor to one of these on its data line, and I won't jumper them around. So the power will jumper around to all of the different motors. But at each motor I will terminate one of these data lines, and then back at the other end of the cable I will have 4 separate LIN bus connections. And what I can do is basically run 4 LIN bus masters, and then depending on which one sends a command, I can control the windows individually. And it also means that I can get results from them individually. So hopefully I'm not going to have crossover, like crosstalk or any problems like that with having these data lines twisted around each other. But I'm going to give it a try and find out. Worst case, if that doesn't work, I can just bond all the lines together and then treat it as one single LIN bus. Now the thing is that I've only got one of those LIN bus shields, so what am I going to do to control them? And also I'm really interested in learning more about how LIN bus works, and I want to make my own nodes. So what I've done is designed a little circuit board that hopefully will give me direct serial communications on the LIN bus. So what I've done is design this PCB, send it off for fabrication, and I should be able to build my own little LIN bus interfaces very soon. The way I've laid out this circuit, I have a serial communications header on this end, because the communications on the LIN bus is typically 19,200 bits a second. It's just a serial bus. So what I've got here is I've laid out the pin header. It's a pin header 6-way, in the same sort of way as you would have a header on an FTDI USB to serial adapter. So what that means is I'll just be able to plug in an FTDI cable or serial adapter and hopefully talk on the LIN bus. So the other end here is I've got this 6P6C connector, the same as I used on these motors, and I've brought it out in the same format So it goes 12 volts, ground, data, data, ground, 12 volts to make it symmetrical. In the middle is this interface IC, which is an MCP2003. What that does is take TX and RX data on one side, and it converts it to the LIN bus standard on the other side, and power comes in through here as well. So VBB is the bus voltage, VSS is the ground reference on the bus. Then I've got power in on this side, so I can just plug in using a DC 2.1mm jack and provide power through the LIN bus to the devices. It's just got power indication and some smoothing. And this is the circuit board layout for the same thing. I've got the FTDI header on this side, so I've got the serial communications, I've got the VIN, which is just used for reference, and ground. These are the smoothing capacitors and LED to show when it's on. Plug in power on this side for the LIN bus power. This is the LIN bus adapter chip, and this is the socket which the cable will plug into. So hopefully I will have those very soon and I'll be able to test them out. If you haven't done much work with communications buses before, there are a couple of things in that last schematic that might make you go, that's weird. There are two things in particular that might really confuse you. This module is designed to be a bidirectional translator. It should just sit in between a regular serial port and a LIN bus connection and allow data to pass in both directions. On the left you can see that there is a transmit and a receive line, which is exactly what you would expect to see. That's what you would commonly see in a normal serial communication system. But on the right there's only one wire. How does that work? If you look at a common serial link between two different devices, each one of them has a transmit and a receive, and they match up. So in this case the device on the left has its transmit output going to the receive input on the device on the right, and vice versa. So if one device wants to send a signal to the other, it's very easy. It simply sends its data on that line and the other end receives it. Piece of cake. We can all understand how that works. But on the LIN bus side, there's only one wire. So how does that work for both transmit and receive? The way it works is a really important concept, and you should learn how this works because it's used in I2C and all sorts of really common serial communication systems. The trick is that neither end or none of the devices that are connected to this bus will drive it absolutely to a high voltage. They will only ever drive it to a low voltage. Okay, once again, you're probably still scratching your head. Look at it this way. Imagine there is a bus and it has a resistor on it which pulls the voltage up to a preset known level. It could be 5 volts or 3.3 volts or 12 volts in the case of LIN bus. Whenever the bus has nothing connected to it that is trying to drive that line to a different voltage, it will just naturally go towards the voltage that it's being pulled to. That's the default that it sits at most of the time. But if any of the devices want to send data on the bus, all they do is ground it. They just pull that line low, which drives it to 0 volts, and then any other device that is on that bus can detect that it has gone to 0 volts. So instead of alternately driving the communications line to either high or low in order to transmit the data, all they do is drive it low or release it, low or release. The result is that if there is a device connected to this and it's not actively transmitting, it'll simply be watching the voltage on that data line, and then it can read the data that might be transmitted by another device at the other end of the wire. And then when that transmitter has finished speaking, it just stops asserting the line, and the other end can then send back a response. This is exactly how systems like one-wire bus and I2C work. So you might have jumped ahead and seen that this also solves our second problem, which is how do you have multiple devices on the bus? Instead of just having one device at each end of a piece of wire, we have a piece of wire with many devices connected to it in parallel. By using the same method, as long as only one device is transmitting at a time, we can have a large number of devices all connected to that same piece of wire. Any of them can send data by just pulling the bus low and then releasing it, which will send it high. And if they stop transmitting, the bus is then available for other devices to send their messages to. So if you've ever wondered why I2C has those 4.7K pull-up resistors on both the clock and data lines, this is why. It's because those lines are biased high through those resistors, and then different devices that are on the bus can just pull the lines low when they want to send data. Hooray, it's PCB day! I always like PCB day. I got a 10-pack like a prototyping pack of PCBs from dirtypcbs.com for the little LIN bus serial adapter board. So now it's time to put some parts on and see if I got it right. Damn, I really screwed this up. Look at the footprint here, which is where the 6P6C connector is meant to go. Look at the mounting holes. There are the 6 connectors in the middle, and then there are the 2 mechanical lugs. But look at the bottom of my socket. It doesn't match at all. And this, boys and girls, is why you should always print out your circuit board on a piece of paper and then test fit the parts on the paper before you get the boards fabbed. That way you avoid problems like this. I think I can fix it though just by cutting these lugs off. Yep, I solved the problem in a nasty hacky way. I just cut the little lugs off and you can see that there's nothing going through the mounting hole now. That 6P6C connector is just held on by the solder joints, which is not ideal, but it's actually still quite strong. So next time I do a revision on this PCB, I'm going to fix the position of those mounting holes. Still should function okay though. What we'll do is start with the module, which will have serial on one side and LIN bus on the other. That will then connect to the motor, which of course also has LIN on it, and I want to supply power down the cable. So I'm going to get a power supply, feed that into the module on that socket that I showed you. But on this side, I want to convert to USB, so I'm going to use a USB to serial adapter, and that is going to connect to my laptop. And what this will allow me to do is send serial connections down through here. It will get converted to LIN, sent down to the motor. This is the module itself. I'll just plug in a power supply of some kind, or 12 volt power supply. Then the cable for this goes to the motor. Unfortunately, all 4 of my motors are currently attached to Windows, so I can't test this on the bench. I'm going to have to go out into the conservatory and plug it all in. And then I've got the USB to serial connector. This could just be done with an FTDI cable. This little adapter basically does the same thing. It's got USB on one side, serial on the other, and then that will plug into my laptop. So with this basic scheme, I should be able to send commands down the serial port and control the motor. So as you can see here, I've got the batteries removed from the motor, and this cable, which is what is eventually going to control it, isn't connected. So I've just got a short length of cable here with 6P6C connectors on it into the LIN bus socket on the motor. And I've also got a plug pack here which is supplying 12 volts. So what I can do is take my little LIN bus interface board, plug in there, plug in there. So this is now powered up, supplying power via the cable to the motor. You may even be able to see that the LED on the motor has turned on. What this should do now is expose a serial connection. So if I grab my USB to serial converter, plug it in, which could just be an FTDI cable, I now have a USB link, and if I open a serial port at 19,200 bits per second, I should be able to talk to the motor. Now I'm using CoolTerm as my terminal emulator because I need to change one of the settings that isn't supported in the Arduino IDE's serial console. We've set the baud rate here to 19,200, 8 data bits, no parity, but we have 2 stop bits instead of 1. Normally you would have 8N1, this is 8N2, and the Arduino IDE can't do that. So we'll close that, we'll open the connection, and now if I type a command which is recognised by the motor, we should be able to make it respond. There we go, we've got a response from the motor saying 200 OK, and you can probably hear that the motor itself is running now, so the window is opening. Now if I send another command like stop, the motor will stop. You can still hear a noise, that's because the little lock is still exercising itself, but the motor has stopped moving the window. And I can do things like send version, and I've got the firmware version coming back now. So now we have serial communications with our motor. So now I should be able to just send the command like close, and the window will respond. There it goes. Here you can see how all 4 pairs from the Cat5 cable come out. The green and orange pairs are the ones that carry the power, and then blue and brown pairs are the 4 data lines. On this particular case there is brown and white, which goes into the connectors. The other data lines just loop through. Each of the 4 motors then has a different one of these data lines tapped out. That way they are all on their own separate LIN bus. I've wired up the motors and you can see that I've put the covers back on for all except one. And that is just so that I can show you how the wiring is done. You'll also notice that they aren't showing the big black mark on them, which is where the infrared receiver is. I thought that looked a bit ugly, and I'm not using the remote control anymore. So all I did was get a couple of bits of white electrical tape, put them over the logo and the receiver, and now it looks much neater and cleaner. So far everything's working out pretty well. So I've soldered up another 3 of these modules, gives me a total of 4, so that I can treat each of those motors as if they're on a separate LIN bus. So let's see how we'll connect it up with an Arduino. So the basic scheme I'm going to follow is something like this. I'll have an Arduino, probably an EtherMega, because what I want to do is connect it to an MQTT broker by Ethernet. And it'll also get power over Ethernet. So this will supply power from the switchboard down through the Ethernet cable to the EtherMega, which is going to be mounted somewhere inside the ceiling. The EtherMega has 4 hardware serial ports. Now this is important because I want to be able to do serial communications to 4 different devices. So then I'll have my little LIN bus modules, and I'm going to have 4 of them, each one connected to a different UART on the EtherMega. And then of course we've got the 4 window motors sitting over here, and each one of those is going to be on the end of a LIN bus connection. Now we also want to get power into these modules. Each one of those needs 12 volts in, so what I'll do is just connect power to the modules and take that off the VIN line on here, and I'm going to be passing 12 volt power over Ethernet to this, so we'll have 12 volts available. And because this is going to be stuck in a little remote place, I'm going to put a watchdog timer on there. That will be connected to the reset on the Arduino, and the output from that will go to the PAT input on the watchdog timer. So if this stops responding for any reason, the watchdog timer will hit reset, and then the Arduino will be booted back into activity. So the board will sit here, got my watchdog timer, got some of these little LIN mods. Now I'm going to wire all of this together on a shield so that it's fairly robust. I'll put some connectors on it, and then I'll be able to mount this inside the ceiling where the cable goes to those motors. Now after going to the trouble of assembling these 4 modules, I've had a bit of a change of heart about how I'm going to assemble this. Part of the problem is how do I get all of the interconnections between the modules and the Arduino and everything else. My original plan had been that what I would do is take the Ethernet cable, which is not actually running Ethernet, that comes out from the motors, separate it, and that I would use a set of 4 of these RJ12 sockets. So I'd split it out, and this would go to 4 sockets, and then each one of those sockets would go into one of these modules. That would be, it's going to be kind of messy on the cable. I don't like that idea very much. But even more importantly than that, it's going to make the interconnections at the back end a little bit tricky. What I can do is very easily connect a single module like this. So I've connected this up, I've run software on the Arduino, and I've proven that this can now send commands to the motor. I haven't shown you that on the video yet, but you'll see that in a little while. So what I'm going to do is take a bit of a different approach. I'm going to terminate the cable from the motors onto a single RJ45 plug, and then I'm going to use this RJ45 breakout and wire this to the modules. So what that means is it's going to look a little bit different. What I think I'll do is mount all of this on a piece of wood, perhaps, maybe a piece of plastic, so that it's all exposed. I'll have the EtherMega there, and then backing onto it I might have the connector here. So this is where Ethernet will come in, this is where the connection to the motors will come in, and then I'll mount these modules somewhere along here perhaps. So what I've done is assembled these other 4 modules, used up a few more of my PCBs, and I made these ones without the connectors on them. So what I can do now is, once these are all physically mounted, just put some jumper wires across them so I can bridge the power connections, and then make some interconnects onto the shield. So I've already assembled part of the shield. There's a watchdog timer module on there, and what that does is take power off the Arduino. It's got an output that connects to the reset pin, and digital pin 2, which comes down through here, is used to reset the timer. If you haven't used watchdogs before, it's probably a good idea to look at my previous episode on watchdog timers. It explains how they work. And also, because I want to be able to disable a watchdog, I've put a jumper on here. This is in line with the connection to the reset. If I pull this jumper off, the watchdog won't be able to reset this. So that means I can do testing and I can load software onto this without worrying about the watchdog timer suddenly tripping and resetting the system. So hopefully that will simplify my assembly process. I won't have quite so many jumper wires, and I'll have a little device that I can then put into the ceiling, and then just have one connection for Ethernet, one connection for the motors. Should make things a bit neater once it's all in place. The pieces are put together on the board, just about ready to go. So this is the setup. Up here you can see that I've got a bench power supply. This is running 12 volts. It's coming out down to here, and I've got an Ethernet switch. This is a power over Ethernet injector. So what we have is Ethernet coming in, power coming in, and then just the single Ethernet cable coming out. That then runs around a bit, comes down to here, and then we have the board which has the Ethermega on it, a shield. I've got the breakout for the RJ45 connector, that's where the motors will plug in, and I've got the 4 LIN bus modules here. And just because I like data, I've stuck a humidity and temperature sensor on here as well. So now if I plug this in, which is pretty difficult while I'm trying to hold the camera with one hand, you can see that it's powered up. So we've now got power on the LIN modules and power on the Arduino and power on the temperature and humidity sensor. Now I need some code on here so that I can use MQTT to control communications on these ports. Oh no, something really bad happened. I let the smoke out of a $100 board. But what's even worse is I didn't have the camera running, so I didn't capture it. It's always when things go wrong that you have the best learning opportunities. Now there are 2 bits of advice that I always give when bringing up a board for the first time. And in fact I did that when I was first connecting this board, but I didn't do it this time. What you do is always, before you connect power, put a multimeter across the power and ground rails and see if you've got a dead short. That's always a big warning sign. Now you'll probably have some capacitance in there from your power supply, but as long as you don't have like a dead short, you're probably okay. The second thing is when you power it up, always power it up on a lab power supply with the current limiting turned on and the limit set fairly low, and then turn the current limit up progressively. That way if you've got some kind of a runaway condition on the board, you're not going to send it up in smoke. However, I didn't do either of those things this time when I was plugging in the extension cable. Now because I didn't want to have to install this inside the ceiling and then connect it all up before I did some testing, I made this little breakout cable. Looks like a network cable, but it's not. It's got the RJ45 connector on this end, which goes into the outputs to the motors, and at the other end, it's got breakouts for the LIN bus. So what I did was plug in power using the Ethernet cable, power over Ethernet. I've got all this turned off right now, but this did have 12 volts on it, so I plugged it in. Everything's running fine. I got my little breakout cable, I plugged it in, all the LEDs turned off, which is a really bad sign. And then a couple of seconds later, I could smell burning and smoke started coming up from the board. I couldn't figure out what was going on for a while because this is just a breakout cable. It takes connections from here, brings them out to the other end and separates them out. There's nothing that's cross-linked here. Every one of these connections is just a link back out. But after a bit of debugging and probing around with the multimeter, I discovered something really surprising. Have a look at this. This is the breakout that was on the cable before I put this replacement in place. So up until a few minutes ago, this was on the cable. And what I've got is positive and negative on these connections here. Now the green you can see here, it's all a bit munged up because I was hacking around with it. Solid green and white which go to two connections on this socket side by side. Now there is nothing else in here, they just go into the socket. I'll just stick my multimeter on continuity test and look at this, or listen to this rather. There's a dead short across these two wires, and all they do is go into this socket and are crimped down. That's it. I've never seen that before, but that was enough to smoke my Arduino. But luckily the Freetronics warehouse happens to be my garage, so it was about 10 steps to the shelf, grab a replacement, and away I go. But it could have been a very, very frustrating and annoying experience. Burning a $100 board is not something you really want to do just because you're rushing and not checking things as you go. Now I started off by putting these parts on this plastic base because I really didn't know what else to do. I just wanted some way to physically mount it while I was working on it and putting all the interconnections in place. But I haven't been able to find a box that I really like, so I'm going to make one. Time to get out Inkscape, get out the laser cutter. I'm going to make some parts and glue it all together, see if we can turn this little bit of plastic into a box. Oh look, got a couple of pieces cut. Let's see if they fit. I'm just going to use super glue or something and assemble this box. That looks like it clears nicely. Sticks out that side. This bit will go on this side. Then I'll just glue a couple of bits on the end and we'll have a box without a lid. Well, it's a bit hacky, but now that the box is ready to go, software is all loaded, it's time to get up into the roof and stick it in place. So this is where I was intending to put it. You can see this is the cable that comes from the motors. This is an Ethernet cable that I dragged through recently, so that goes through to the switchboard. But now that I'm up here, I've changed my mind. I'm not going to mount it here at all. It was going to go just up here somewhere. But being in here really sucks. Now, my ceiling space is probably about the nicest ceiling space you'll ever see. I mean, I'm sitting on a carpeted walkway here. I've got lighting wired up through here. I mean, it's linked to my home automation system, so from my phone, I can turn these lights on and off. Spooky! So I actually have home automation control inside my ceiling space, and yet it's still a really nasty place to install something. When I started doing home automation, I used to put devices in all sorts of crazy places, like under the floor and in the ceiling and in walls and just in strange places. And over the years I've realized how much of a pain that is. So once again, I've got all these rules. 3 rules now for when I want to find somewhere good to install something. First rule is I shouldn't need a ladder to get there. Second rule is I shouldn't have to crawl through, get down on my hands and knees. Third rule is I shouldn't get so dirty that I need a shower afterwards. Now, I break all 3 of those rules by mounting it up here. It might make sense to take a little device and mount it somewhere obscure, but if you can mount it somewhere that you can walk up to it wearing nice clothes and work on it, upload new firmware and all those sorts of things without getting yourself dirty, then that's so much better in the long term. So I'm going to go to the trouble of actually getting the motor cable through to my switchboard area and maybe mount it down there. Now, LIN is supposed to be able to do a 40-meter cable run, and once again, I don't know if I'm really pushing the limits here with noise and crosstalk and things, but I'm going to give it a try. So I'm going to run that cable down to the switchboard and put it down there instead, and then I don't have to come up here just to do a firmware update. So instead of mounting it up inside the ceiling, I've decided to mount it here. This is one of the secondary switchboards which is used for distribution of network cabling, and it has connections to the light switches and various other things around the house. It's a much easier place to get to. I can just walk up to it. Power is available here. And here you can see the cable that I've dragged down. This is the blue cable that was up inside the roof that I was just showing you a moment ago. But the end of it I've pulled down through the ceiling and threaded through to here. So that goes to the 4 motors in the conservatory. On the other side there is this network cable which comes from a power over Ethernet injector, and that way I've got 12 volts coming down the network cable providing power to this controller, which then controls the motors. Now we're finally ready to test it. The controller is in place, firmware is loaded, it's powered up. I've just used some electrical tape to pull the excess cable back out of the way. In fact, I've coiled it up in the battery compartment because there was some space there. I don't need the batteries anymore. Now I can try sending a command to the MQTT broker. The controller should pick it up, send a command to the window. So let's see, conservatory window 2, open, and let's see what happens. I can hear it responding, it's doing its unlock, and it started opening. So it looks like we've got some degree of success at least. So I'll see if I can stop that one now. Yeah, I've stopped it opening. The lock mechanism is still exercising. And open again. Cool, I can control the windows. Now unfortunately a bit of testing has revealed a problem. If I send a command to all 4 windows at the same time, which is sending out the LIN bus message on serial ports 0, 1, 2 and 3, sometimes some of them respond, some of them don't. So I've had to mess around a little bit with it, and I think what is happening is that there is crosstalk between the different data lines. Because it's twisted pair, what's happening is that the data lines for 2 of the motors are twisted together very tightly, and that will inductively couple them together. So when a command is sent on one, it will have like a slight influence on the wire that is sitting right beside it. And if I send a message on both at the same time, it can cause a little bit of interference. It could also be related to power. Because there are 4 motors here, if they all start at the same time, there will be inrush current on the motor, there could be a voltage drop. So what might be happening is that we've got a voltage drop situation that is causing some of the motors to read the message and then some of them to fail. So at the moment, if I hit the all open, you can hear that one started. None of the others have started. I'll hit all open again. And now that one started, this one started, and the one on the far side has started. So I can control them all, I just can't send messages to them all at the same time. So when faced with a problem like this, I can think of 2 possible causes. There is the crosstalk that I just mentioned and the power droop. Now to try to eliminate that, what I did was use some jumper wires and I bridged across all of the LIN connections, disabled 3 of the modules and just ran one module with all 4 of the data lines essentially bonded together into a single LIN bus. As we saw before, that means I can't address the motors individually, but if I send, say, an open command, all of them will respond. And I did that, and all of the motors worked 100% reliably. I could send open, they would all open, close, and they would all close. Now, if it had been a problem with power droop on the motor starting, I would have seen the same symptoms as before. But because all of the motors start reliably when they're all on the same LIN network, I'm pretty sure that the problem is crosstalk. Now, the only way to really tell is going to be to stick an oscilloscope on a couple of the data lines. So what I could do is put probes on 2 of the lines, send a command on one of them, and see if I get a similar signal on the other line. So I found that by messing around with the code a little bit, I've just hacked the firmware slightly to add a delay. So when I send a command to all the motors, what it actually does is send a command to the first motor, wait a quarter of a second, send it to the second motor, wait a quarter of a second, and that has made it a whole lot more reliable. Now this video has highlighted quite a few changes of plan since the project began. There have been a whole lot of stuff ups and I just changed my mind about a few things. I failed at controlling the motors individually on one LIN bus, which was really disappointing. And I also burnt an Arduino, which is not fun either. I changed my mind about mounting it in the ceiling, decided to put it down in the switchboard instead. And because I changed the breakout from using RJ12s to the single RJ45, it meant that the sockets that were on my breakout modules were no longer what I needed, and I had to put a second breakout in there to make that work. So there are a whole lot of things that didn't work out. And of course I've got the crosstalk or the power problems, which I'm going to have to resolve. So I could have made this video about half as long by cutting out all of those missteps and changes of direction and just showing you the end result. But part of what I wanted to show is that projects like this aren't just about getting an end result. There is a sequence that you go through as well. Often you have to feel your way out, work out what is working and what's not working, and change your plans along the way. You need to be able to adapt. So if something isn't working out, try to find an alternative solution to it. A lot of projects will go smoothly, but a lot of them won't. So you need to be ready for that sort of thing. And don't feel bad if you start working on something and it doesn't work out as you expect. You might have to go back and rethink your plans, come up with a new solution to the problem. I do that all the time. Almost nothing that I build works out how I expected it to the first time. Now the software that I have running on the controller isn't very pretty, but it works. So what it does is connect to an MQTT broker, listen for commands, and then send messages down the LIN bus to the motors. It starts off by including some libraries that it needs for networking and for talking to MQTT. It sets up some networking configuration here. I don't need to go into this in too much detail. So what it does here is subscribe to a topic called conservatory/windows. This is where it will receive commands that it needs to send out. It also has another topic called events, and that's where it just publishes updates so we can see what it's doing. Then we set the address of the MQTT broker, which is running on a Raspberry Pi on my network. I've got a watchdog timer on here as well, so I've got some set up for that. I've also got that DHT22 temperature and humidity sensor. So it defines the type of sensor and sets up some MQTT topics so that it can publish readings from those sensors. And here is the LIN message delay. This is so that it can send a message, wait a quarter of a second, and then send the next message. Once we get down into the callback, you can see that there are a whole lot of lines that are commented out. These are echoes to the serial port so that I could do debugging early on. I commented them out because I'm using that serial port now to talk to a LIN module. So what happens in this callback is that if there is a message published to the command topic on MQTT, the message itself ends up coming through here, and we look at the first character, which is character 0, and the third character, which is character 2, and they are taken as being the ID of the motor and the command that needs to be sent. So if we were sending a command to motor 1 and we wanted to say open, then it would be 1, 1, because it's motor 1 and command 1. So all this callback does is examine the motor ID, and then it makes a call out to a different function depending on which motor has been called. This could all be rationalized, probably done in a single function, but this is just the way it's structured at the moment. So we set up some objects for the network, the MQTT, and for the temperature and humidity sensor. Here we have a function that attempts to reconnect to MQTT, and it just keeps trying over and over again every 5 seconds until it gets through. The setup function starts with some commented out debug information. Once again, we can't use that because serial port 0 is being used to talk to a LIN module. Then if the watchdog is used, it sets up the appropriate pins. If the MAC address ROM is being used, it reads from the ROM and then it writes it into that array. Then it starts networking. If we've got DHCP enabled, it uses it, and it sets up the connection to MQTT. Then this is where things get interesting in terms of LIN. What we do is open the serial ports and we pass in this configuration parameter. Now normally when you do a serial begin in Arduino, you just pass in the baud rate. But in this case I've passed in a second argument, which is a special configuration option. This tells it to go into 8 data bits, no parity, and 2 stop bits. And that's what we need for these particular motors. If you don't specify this, it defaults to 8N1, not 8N2. The loop doesn't really have very much in it. It just tries to connect to MQTT, process the client, and run the heartbeat. Any incoming commands that this needs to process from MQTT are handled by the MQTT callback, and that's why we have client.loop here. Run heartbeat is only required because I've got a watchdog timer and because I'm periodically reporting back sensor values. This wouldn't be needed at all if there was no watchdog. So what the heartbeat does is just check whether the timeout has expired since the last watchdog has been reset, and if it has, reads from the sensor, publishes, and then resets the watchdog timer. And down here we get into the motor functions. Motor 0 is all motors, and then motor 1, 2, 3 and 4 are the individual motors. So what we do here is look for the command. In this particular case, the command of 1 is open, so it sends a command of stop to begin with and then an open command to the first motor, and then it does the same for each of the subsequent motors. And it just has this delay in between of LIN message delay. The individual motors are a little bit simpler. It just sends the message to that motor only, doesn't have to send it to all of the others. Motor 2, motor 3, motor 4, all pretty much the same. Then we have the pat watchdog function, which just pulses the watchdog pin so it resets it, and it just resets this variable so that it knows the last time that it reset the watchdog. And it finishes off with a read register function, which is just used for I2C communication to the ROM to read the MAC address. Now that it's mounted down here in this little telco cupboard, am I satisfied with the result of this? Hell no. All of those wires, those interconnects are horrible. One of the things I've learned out of building many of these sorts of projects is that every wire in your system, every interconnect, is a potential problem. This is really just a proof of concept. It's a few modules that have been hacked together, and I really need to make something that's more integrated for future use. So in a future video, what I'm going to need to do is do an update on this. I'm probably going to lay out a whole new circuit board that integrates the connections for all the different LIN buses all on one board. I don't want to have jumper wires like that, and I want to make it into a really nice case, probably something that'll be rack mountable, certainly not just a few individual modules like that screwed onto a piece of plastic. I can't leave it hanging there because it just won't be reliable. So we'll follow that up in a later video, but for now, go and build something cool. See ya.